Okay, question 9 of the applied questions for Chapter 3 of An Introduction to Statistical Learning. This video will use Python code. I've made another video that uses R code if you are more comfortable with R or want to learn R instead. Having said that, let's get into the question. So we are once again going to be doing regression like we did in question 8, but in question 8 we used single variable regression, right? We just regressed on horsepower on a single variable, and now we're going to be regressing on all of the variables in the data set. And so we will get to that. There's a few things that the question asks us to do ahead of time, and some things that it wants us to do after. So we'll just kind of tackle these one at a time instead of reading everything all at once. So first, make sure that you have the ISLP library installed and imported on your machine. And then we also need all of these different libraries. And once we have those libraries in there, we need to load the auto data set. And the question is going to have us omit one of the variables in that data set, namely name. And so we're going to be working with a truncated data set that is called auto subset, or that I have called auto subset. You can call it whatever you want. Okay, so I've already ran that code, so I'm not going to replicate it. But part A wants us to produce a matrix of plots that shows the relationship between each of the variables. Okay, and so the way that I do that is with this pair plot function. Okay, and it takes a second to run, I guess. Okay, still thinking. Maybe I'll pause it. Okay, we're back. It took, I don't know, 15 seconds to run or so. What we have is, so along the vertical axis here, we have all of the different variables in our data set. And then wouldn't you know it, we have them again on the x-axis. And so when we want to find the relationship between any of the two variables, we would go to, so let's say I wanted to find one between acceleration and displacement. So I would go to acceleration as a row and displacement as a column, and it's right here. Okay, I could do it the other way. I could go to acceleration as a column and then go up to displacement. Where's displacement? Displacement is right here as a row. Okay, so those two plots should be identical. All right. Now part B, we want to, this is a graphical representation of these different relationships, but now I want to find the correlation between them. Okay, and so the way that I find my correlation matrix is with the core function, and I'm rounding to 2 decimal points so that we're not trailing 10 digits in the background. So here is my correlation matrix. Okay, it's actually set up very similar to the pairs plot up here. So again, if I want to find a correlation between, say, acceleration and horsepower, I go to the row of acceleration and over to horsepower. Okay, 0.69. Or I could do it the other way. I could go to the horsepower row and then the acceleration column, right? And notice that they're both the same value, right? So this matrix is symmetrical. Okay. Also notice that that every correlation of a variable with itself, cylinders and cylinders, miles per gallon with miles per gallon, is always 1. So down the diagonal, there's always a 1. And then the last thing I want to say about this is, in the next part of the question, we are going to run regression of miles per gallon on each of these predictor variables. Okay. And that regression is going to estimate the relationship between miles per gallon and the other variables. And you might think that sounds a lot like correlation. And it is a lot like correlation as we have here, but there's a difference. In regression, the associations that are estimated, the beta coefficients, if you're familiar with that terminology, represents something closer to a partial regression. What's a partial regression? A partial regression says, so let's take cylinders in miles per gallon. It would say that that the correlation between cylinders and miles per gallon after accounting for every other variable in the regression is whatever the estimate is. Okay, and it's that after accounting for every other variable that's important here, because a correlation matrix does not account for all of these other variables. It's just a raw correlation without considering how all of the other variables are related as well. Okay. So part C, scroll back up here to my questions. So now we're actually going to perform linear regression here. And it asks us to use some specific functions, but I don't particularly like those functions, so I'm doing something different but accomplishing the same thing. Okay, so let's see here. Where are we at? Okay, C. So we're using ordinary least squares algorithm. Okay, so what do I need to do? So I need to subset. My data. But I'm dropping now the miles per gallon because that's going to be my outcome variable. So I've created a matrix basically that doesn't have the miles per gallon, and I'm using miles per gallon as my outcome, as my y variable. I'm also adding a constant to the matrix x that just represents, that will help us or will allow us to estimate the intercept of the model. Okay, so now I'm just fitting my my ordinary least squares model, and what I get out is the summary. Okay. Again, in the previous question, we went through some of this, and the important, well, for our purposes right now, the important bit is contained in this table here. All right. So we're asked to go through and determine which variables have a relationship with miles per gallon. So I want to say a couple of things here. First of all, I don't like the way that question is phrased, and maybe it's meant to elicit that response in us. But what we have is a sample of data from a bunch of possible data that we could have collected, and we have assumptions embedded in the model. Okay, and what we get is a bunch of coefficients here, and these coefficients represent our best estimate of the association between the two models. So in a way, unless it was 0.0000000 with a very low p-value, we wouldn't be really confident saying that there was no association between these things. Okay. Instead, what we get is that we estimate that the relationship between any of these variables with miles per gallon is what's given by the coefficient plus or minus the standard error given over here. It is then a separate question for us to ask, how confident are we in that estimate? And that confidence is partially summarized in our p-value, where low p-values suggest higher confidence. Okay, so that's the way probably we should think about relationships that are pulled out of the regression. Okay. We're also asked specifically to comment on year. So here we have the year entry. So we see that one, we have a very low p-value, rounded to 0. It's not 0, but it's rounded to 0. So whatever our finding is, we're going to have fairly high confidence in it. And that relationship is that that newer cars, for every 1 year newer, a car has 3/4 miles per gallon more or better gas mileage, plus or minus 0.05. Okay. Oh, so part D. Geez, a lot of scrolling. So now we want to produce some diagnostic plots to see if our model is fitting fairly well or not. So I'm going to go down to D. So in R, this is so much simpler. All these plots can be rendered in just one line of code, but that's okay. So what we have here, just like we saw in question 8, I would suggest maybe you go look at question 8 to help interpret these plots. But let's go through these. So first we have residuals versus fitted values. So each of these dots is a residual from the regression, which again is kind of like it's the error in prediction from the model. And what we see is that as we go from left to right, that error gets larger. And so this is violating one of our rules of or assumptions of linear models, of normal linear models anyway, simple linear models, where the variance should be constant across all of these different fitted values, okay? We also see maybe like a curvilinear relationship in here, which is also a problem. It suggests that there's some structure remaining in those residuals. In other words, there's another variable or something, another assumption that we need to make to get rid of the pattern in these residuals, okay? Here's our QQ plot. It looks a little bit exaggerated here, but nevertheless, we see quite a bit of deviation away from normal. In fact, I think that is wrong. I'm not going to correct it right here, but I think that's actually incorrect. I think there's something weird here in the code, but that's okay. I'm not going to worry too much about it right now. I don't think it's as bad as it's being shown here. Anyway, and then lastly, we have Cook's distance. Okay, so the Cook's distance is basically how much each observation is in charge of determining the fit of the regression line. And that's a weird thing to say. But when you have few observations that are highly determinant of the regression line, it suggests that maybe either that's an outlier or that the model is not doing a good job of capturing the data. Okay, and so if here we have a few high Cook's distances, or much higher than the rest, and these are observations that have an undue influence on the fit of the regression line. And so we would probably want to go through and investigate these lines and investigate the assumptions of our model, because these suggest that our model is not doing a good job with our data. So either the data is faulty or our model is faulty. Okay. Okay. E and F. So E asks us to put some interaction terms in there. So I've used this formalism right here, and there's a couple of ways to get interactions here. One is with an asterisk, the other is with this colon, and I'm also using a slightly different formula or command here. But the difference. So a few things to say here. The difference between the asterisk and the colon is when I use an asterisk. So here's cylinder and displacement. If I go down here, I notice I get the cylinders and displacement interaction, and I also get the cylinders main effect and the displacement main effect. But if I go to the horsepower colon weight, I get the interaction but not the main effects, and so that's the difference between the two. Okay, we see that a lot of these interactions are significant, but I wouldn't take that too seriously, because what does significant mean? I've kind of haphazardly made this model. So just because they're significant, unless there's hold on, let me clear my throat. Unless there's reasons to trust the assumptions in the model, there's also, there's no reason to trust the estimates that come out of the model. Okay. Okay. So finally, we also want to transform. The last thing that it asks us to do is to transform the x variables in these different ways: log, square root, square. And rather than do that to every variable, I'm just going to replicate the regression from question 8 with just a single variable. But I'm going to log it and square root it and square it. What did I say? Log, square root, square. Okay. And I'm just going to I'm going to make a point here, and I'm just going to print the coefficients. Okay. And what we see is that the coefficients for each of these models is pretty different. But of course they're different, okay, because I've put in different data. I'm no longer putting in horsepower, I'm putting in the log of horsepower. Those are different numbers. Square root of horsepower is different than horsepower, etc. And so I don't really, so of course there's differences. Now what's important here, and I'm running out of time so I have to hurry, but what's important here is that one of these models may be better than another. And one of the ways that we would start to determine that is to go through with these diagnostic plots with each of these models, which I'm not doing here, but to see if we alleviate some of the fitting issues with this or that transformation. Okay, there's going to be more to say about transformations eventually, but that is it for now.